Touch a metal doorknob in winter. Cold. Now touch the wooden frame next to it. Warmer. They've been in the same room for hours. Same temperature, so why does one feel colder? Your body is lying to you, and what you think you know about heat, cold, and temperature is completely wrong. This isn't about science trivia. This is about reality. The physical world doesn't work the way your senses tell you it works. And temperature, something you experience every single day, is not what you think it is. Let's start with what just happened. You touched metal, you touched wood, one felt colder. Your brain immediately concluded the metal was at a lower temperature. That conclusion was false. Both objects were at exactly the same temperature. So, what did you actually feel? Not temperature. You felt the rate of heat transfer. Heat was flowing out of your hand, into the metal, into the wood, but at different speeds. The metal conducted heat away from your skin rapidly. The wood conducted it slowly. Your nerve endings don't measure temperature. They measure how fast your skin is losing or gaining heat. That's a completely different thing. But your brain interprets it as temperature, and that interpretation is wrong. This is the first lie, the lie of sensation. Everything you've ever felt as hot or cold was actually thermal conductivity, not temperature. You've never felt temperature directly, not once in your entire life. So, what is temperature? The standard answer: a measure of how hot or cold something is. That answer is circular, meaningless. It defines temperature using the words hot and cold, which themselves refer to temperature. We need to go deeper. Temperature is not heat. That's the second thing you need to understand. Heat and temperature are different. Heat is energy, thermal energy, measured in joules. It's the actual physical quantity flowing between objects. Temperature is something else. It's related to heat, but it's not the same thing. You can add heat to something without changing its temperature. Ice melting at 0 degrees Celsius, you're adding energy, but the temperature stays constant. The energy is breaking molecular bonds, changing the structure from solid to liquid, not raising the temperature. Heat is flowing in, but temperature isn't rising. They're not the same thing. So, if temperature isn't heat, what is it? Here's the answer. Temperature is an average, a statistical property of many particles moving. Not a thing in itself, not a substance, an average. Everything is made of atoms, molecules, particles too small to see. And those particles are moving, always. In a gas, they're flying around, colliding with each other. In a liquid, they're jostling, sliding past neighbors. In a solid, they're vibrating in place, oscillating around fixed positions, but always moving, never still. The temperature of a substance is related to the average kinetic energy of its particles. Average, that word is critical. A single molecule doesn't have a temperature. Temperature only exists for collections. For systems with billions and billions of particles, it's a statistical concept. When you say this room is 20 degrees, you mean the average kinetic energy of air molecules corresponds to 20 degrees. But individual molecules have a huge range of energies. Some are moving slowly. Some are screaming through space at hundreds of meters per second. The temperature is just the average. It hides all that variation. Think about a molecule of nitrogen in the air right now. It's traveling at about 500 meters per second, faster than the speed of sound. Why don't you feel wind from these molecules? Because they're going in random directions, no net motion. Just chaotic thermal movement. That molecule collides with other molecules billions of times per second. Each collision changes its speed, its direction. Sometimes it speeds up, sometimes it slows down. On average, over countless collisions, its energy stays constant. And that average, that statistical property across trillions of molecules, that's what we call temperature. You're not measuring a thing, you're measuring an average of motion. Temperature is an emergent property. It emerges from the collective behavior of particles. It doesn't exist at the level of individual atoms. One atom doesn't have a temperature. It has kinetic energy, momentum, but not temperature. Temperature requires a collection, and it requires equilibrium. If a system isn't in equilibrium, temperature isn't even well defined. This is subtle but important. Temperature is a macroscopic concept arising from microscopic motion. But it's not reducible to any single particle. You can't point to a molecule and say that molecule is hot. You can only say the collection has high average kinetic energy. Now let's talk about cold. What is cold? Most people would say it's the opposite of hot. The presence of coldness, but that's wrong. Cold is not a thing. There's no cold energy. There's no substance called cold flowing between objects. Cold is just the absence of heat, like darkness is the absence of light. When you turn off a light, darkness doesn't flow into the room, there's just less light. Same with cold. When you touch ice, cold isn't flowing into your hand, heat is flowing out. The ice isn't giving you cold, you're giving it heat. Heat always flows in one direction, from hot to cold, always. That's the second law of thermodynamics. Entropy increases. Heat spreads out. This is not a suggestion, it's a law. When you hold an ice cube, heat flows from your warm hand into the cold ice. Your hand cools down, the ice warms up. Eventually they reach thermal equilibrium. Both at the same temperature, then heat flow stops. Not because there's no more heat, but because there's no more temperature difference, no driving force for transfer. The ice melts because it's absorbing heat from your hand. That heat breaks the bonds holding water molecules in a rigid structure. The molecules gain energy, start moving more freely. Solid becomes liquid, but here's the key. The temperature of the ice stays at 0 degrees during melting. All that heat energy goes into breaking bonds, not into raising temperature. Temperature measures average kinetic energy of random motion, but energy can also be stored in other ways. In molecular bonds, in rotational motion, in vibration. Temperature is just one piece. Now back to that metal doorknob. Metal and wood, same room, same temperature. Why does metal feel colder? Let's go deeper. Your skin is at about 33 degrees Celsius. The room is at maybe 20 degrees. When you touch the wood, heat flows out of your skin. But wood is a poor conductor. Thermal energy moves slowly into it. The surface layer of wood warms up quickly, because wood doesn't conduct heat away from that surface rapidly. The boundary between your skin and the wood reaches a compromised temperature, higher than the wood's initial temperature. Lower than your skin's, your nerve endings detect a modest drop. Feels cool, but not freezing. Now the metal. Metal is an excellent conductor. Heat flows out of your skin rapidly. The metal whisks that heat away from the contact point efficiently. The surface stays cold because heat is being conducted into the bulk of the metal. The interface temperature stays much lower. Your nerve endings detect a rapid, substantial temperature drop. Feels very cold, but the metal and wood started at the same temperature. What you're feeling isn't temperature, it's thermal conductivity. How quickly the material steals heat from you. This tells you something profound. You've never felt temperature directly. Never. Every sensation of hot or cold you've ever experienced was actually about heat transfer rate. Thermal conductivity, not temperature. Your senses evolved to detect danger. Rapid heat loss can damage skin. Rapid heat gain causes burns. So your body detects those, not temperature. Temperature is an abstraction, a scientific concept, not a sensory experience. Let's talk about how we actually measure temperature. Thermometers. What do? They don't measure heat energy directly. They measure some property that changes with temperature. Mercury expands when heated, contracts when cooled. Put mercury in a tube, mark the levels at different temperatures, and you have a thermometer. But the scale is arbitrary. Celsius chose the freezing point of water as 0, boiling point as 100. Convenient for water, arbitrary otherwise. Fahrenheit chose different reference points. 30 for freezing, to 12 for boiling. Different numbers, same physical reality. Kelvin used absolute 0, the coldest possible temperature. 0 Kelvin means 0 kinetic energy. Molecules stop moving. Can't get colder than that. At least not in conventional physics. All these scales measure the same thing. Average kinetic energy, but they assign different numbers to it. Temperature is a human construct, a way of quantifying something real. But the numbers themselves are arbitrary. Absolute 0, 0 Kelvin. Minus 273.15 degrees Celsius. At absolute 0, classical thermal motion stops. No vibration, no rotation, no translation. Quantum mechanics complicates this slightly. Heisenberg uncertainty. 0-point energy. Particles can't be completely still, but thermal motion as we understand it ceases. This is the limit. You can't go lower. There's no negative temperature in the conventional sense. Well, there is, but it's strange. Systems with negative Kelvin temperatures are actually hotter than any positive temperature. Population inversion, more particles in high-energy states. Not relevant here, but worth knowing. The point is absolute 0 is the bottom, where temperature stops having conventional meaning. Now let's emphasize something again. Temperature is statistical. This is the key to understanding what it actually is. Imagine a box with 6 gas molecules. You can track each one individually. Molecule 1 moving at 400 meters per second. Molecule 2 at 600, 3 at 300. 4 at 500, 5 at 700, 6 at 200. What's the temperature? You calculate the average kinetic energy. That gives you a number. But is it meaningful? 6 molecules isn't many. The average fluctuates wildly. One collision could change everything. Temperature is only meaningful with large numbers. Avogadro's number, 6 times 10 to the 23rd particles. With that many, the average stabilizes. Fluctuations become negligible. Temperature becomes reliable, but it's still an average. Still a statistical construct, not a fundamental property of individual particles. This makes temperature an emergent property. It emerges from collective behavior. It doesn't exist at the atomic level. Individual atoms don't have temperature. They have kinetic energy, momentum, position, but not temperature. Temperature requires a collection, a system, and equilibrium. Let's return to heat. Heat is energy transfer. Not energy itself, transfer. If the objects are at the same temperature, no heat flows between them, even though both contain thermal energy. Heat is energy in transit, from hot to cold, driven by temperature difference. No difference, no flow. You can have high thermal energy with no heat transfer. A hot object isolated in space, lots of internal energy, high temperature. But no heat flow because there's nothing to transfer to. Heat requires a gradient, a difference. Heat transfers in 3 ways: conduction, direct contact, molecules colliding, energy spreading. The metal doorknob, heat conducted from your hand into metal. Convection, bulk motion of fluids, hot air rising, carrying energy with it, boiling water. Heat transferred by moving liquid. Radiation, electromagnetic waves, photons carrying energy through space. The sun warming your face, no contact, no medium. Just photons transferring energy, all 3 are heat transfer. All driven by temperature differences. All trying to equalize temperature. The universe wants equilibrium. Heat flows until everything is the same temperature. Then it stops, thermal death of the universe, eventually. But not yet. At very low temperatures, quantum mechanics takes over. Classical ideas break down. Particles stop behaving like little balls. They become waves, probability distributions. Temperature still relates to energy, but the relationship gets complicated. Bose-Einstein condensates, atoms cool 2/1000ths of a degree above absolute zero. They collapse into the same quantum state, behaving as one coherent matter wave. Temperature near zero, but individual particle motion doesn't quite apply anymore. Quantum statistics take over. Fermi-Dirac statistics, Bose-Einstein statistics. Different rules for different particles. Temperature is still statistical, but the statistics are quantum now. Not classical, even temperature, this everyday concept gets strange at extremes. There's also an upper limit, the Planck temperature. About 10 to the 32nd Kelvin, the hottest possible temperature. Beyond that, our physics breaks down, quantum gravity effects dominate. Space and time themselves become uncertain. Temperature loses meaning. This was the temperature of the universe immediately after the Big Bang, 10 to the minus 43 seconds after the beginning. The earliest moment we can describe before that, we don't know. Our theories fail, so temperature has limits. Absolute zero at the bottom, Planck temperature at the top. Outside those bounds, the concept doesn't work. Inside them, it's a statistical average of particle motion, useful, predictive, but not fundamental. Is temperature real? That's not a trivial question. It's emergent, statistical, a human-defined scale. But it has real effects. You can predict system behavior based on temperature. Chemical reactions depend on it. Phase transitions, melting, boiling, freezing, all temperature dependent. So temperature is real in the sense that it's useful, predictive, measurable, but is it fundamental? No, it's derived, emergent, built on top of more basic physics. Particle motion, kinetic energy, statistics, temperature is what happens when you average over that. It's real the way average is real. The average height of people in a room is a real number. You can measure it, use it. But it's not fundamental. It's a summary. Temperature is the same. Thermodynamics treats temperature as fundamental. One of the basic variables, temperature, pressure, volume. The macroscopic description, from this view, temperature is real, primary, statistical mechanics goes deeper, derives thermodynamics from particle motion, shows temperature is an average, both views are valid. Depends what you're trying to do. If you're designing an engine, thermodynamics is enough. You don't need to think about molecules, temperature, heat, work suffice. But if you want to understand what temperature is fundamentally, you need statistical mechanics. You need to see it as emergent, as the macroscopic manifestation of microscopic chaos. Let's revisit that beginning. Metal and wood, same temperature, different sensation. Now you understand why temperature is average kinetic energy of particles. Both materials have the same average, but thermal conductivity is different. How fast heat moves through the material. Metal has free electrons carrying heat efficiently. Wood doesn't. Heat moves slowly. When you touch them, you're not measuring their temperature. You're measuring how fast they steal your heat. Your senses detect the rate of change, not the absolute value. This is why a pool feels cold even when it's warm. Water conducts heat better than air. Even warm water pulls heat from your skin faster than warm air does. So it feels cooler even at the same temperature or warmer. Your sensation is not a thermometer. It's a heat flux detector. Wind chill, another deception. Minus 10 degrees with wind chill. What does that mean? Air at 0 degrees moving at 30 kilometers per hour feels like minus 10 in still air. But the temperature is still 0. The air isn't colder because it's moving. Wind chill isn't a temperature. It's a measure of heat loss rate from exposed skin. Moving air removes the warm layer near your skin, replaces it with cold air continuously. Heat loss accelerates, feels colder. But actual temperature hasn't changed. Wind chill is a sensation index, not a temperature reading. This distinction matters. Your pipes won't freeze faster because of wind chill. They freeze based on actual temperature. But we confuse the two because sensation feels like temperature. It isn't. What does all this mean? Our intuitions about temperature are wrong. Built on sensation, not physics, temperature isn't a thing you feel. It's a statistical property of particle motion. Heat isn't a substance, it's energy transfer. Cold isn't the opposite of heat. It's the absence of it. These aren't semantic games. They're fundamental misunderstandings about how the world works. We use words like hot and cold as if they refer to simple direct properties. They don't, they refer to complex statistical averages of microscopic chaos, filtered through the unreliable sensor of human skin, interpreted by a brain evolved for survival, not accuracy. Your brain is Bayesian. It predicts, infers, guesses. When you touch something, your brain doesn't passively receive temperature data. It predicts what it expects based on context, then updates based on sensation. This is why the same water can feel different depending on what you touched before. Touch ice, then room temperature water. Feels warm. Touch hot water, then room temperature water. Feels cool, same water. Different perception. Your brain isn't measuring absolute temperature. It's measuring change, difference, surprise. Actual temperature is almost irrelevant to experience. What matters is expectation violation. Temperature perception is relative, contextual, unreliable, not absolute. Science corrects for this. Thermometers don't care about context. They measure a physical property consistently. Expansion of mercury, resistance of wire. Blackbody radiation, different methods, same target. Average kinetic energy of particles. This is what science does, replaces unreliable sensation with reliable measurement. Replaces intuition with mathematics. Replaces feels cold with 17 degrees Celsius, objective, reproducible, communicable. This is how we transcend sensory limitations by building tools, developing theories, testing them against reality. Temperature is real because we can measure it consistently, predict with it, derive consequences, not because we feel it. So, what is temperature after everything we've discussed? A measure of average kinetic energy, a statistical property of large particle collections, an emergent phenomenon from microscopic motion, a macroscopic summary of submicroscopic chaos, a number on an arbitrary scale, useful, predictive, real in its effects, but not fundamental, not a thing in itself, not what you feel when you touch something. Temperature is an abstraction, a human concept imposed on physical reality. It works because it corresponds to something real, average molecular motion. But the concept itself is ours, the scale is ours, the interpretation is ours. Nature doesn't care about Celsius or Fahrenheit. Molecules just move. We measure, average, assign numbers. Call it temperature and use it to predict the world successfully. That's what temperature is. Touch the metal doorknob again. Feels cold. Now you know what that means. Not that the metal is colder, but that it's conducting heat away from your hand rapidly. The sensation is heat flux, not temperature. The temperature is just average kinetic energy of the metal's atoms, same as the wood next to it, both vibrating at the same average rate. But one steals your heat faster, that's all, no mystery, just physics. Microscopic motion creating macroscopic sensation. Statistical mechanics dressed up as feeling. Temperature isn't what you think it is. It never was, but now you know what it actually is. An average, a measure, a useful fiction. Real in its consequences, but not in the way you imagined, and maybe that's true of everything. The world isn't what it seems, sensations lie, intuitions mislead. Only measurement and mathematics reveal what's actually happening. Temperature was just one example, but it's everywhere. Everything you think you know about the physical world, most of it is wrong, or incomplete, or oversimplified. The real world is stranger, more subtle, more statistical than you think, but that's what makes it interesting. That's what makes it worth understanding. Not the comfortable illusions, but the uncomfortable truth underneath. Temperature is an average of particle motion, nothing more, nothing less. And now you can't unknow that. Every time you feel cold, every time you touch something hot, you'll remember the sensation is lying. The particles are just moving, and temperature is just a number we made up to describe that motion, a useful number, but still just a number. That's what temperature is. That's all it ever was.